There it goes. Okay. Well, for this chapter, chapter 6 on thermochemistry, somehow I built in a huge amount of buffer. So maybe I didn't expect to finish the lecture last week. But as it turns out, we have available to us today and Wednesday for review. And the test won't be until after we get back on the 23rd. So you got plenty of time to work on thermochemistry. That may be good for some of you. I mean, it's giving you fits or just minor problems that tend to be a constant irritant. Then you have more time to work through the problems. And I'm going to be here next week in my office. And I'm pretty sure the building will be open. So if you want to swing by or call me, or we can set up a Zoom session, whatever you need. And anything that crops up between now and 23rd, we can deal with it before then. Okay. So let's see, thermochemistry, and I'm pretty sure, yeah, we finished the lecture. So we're ready to look at review problems. Let me pull those out. Like this. Yeah, okay, we're good. Here. Here we go. All right, so the floor is open for specific problems. And we got the better part of an hour left today. And then Wednesday, we can do a little more review if you need, or we can do just a little bit of review on Wednesday and then go in the lab so we have plenty of time to do the lab. So, specific problems. Anything giving you fits? Or inquiring minds want to know? No? Well, when all else fails, we start at the top. So I'll just run down the review document, and when we get to one that we've done before, I'll just skip it, unless you stop me and insist on doing that one. So we'll start off with number 1. Okay? Okay, so what are we given? A gas absorbs 0.0 joules of heat. So our Q value, 0.0 joules, right? And since it's 0, the sign doesn't matter. It says absorbs 0 joules of heat. It's kind of oxymoronic, I would say. But it also performs 30.7 joules of work. If it performs, what does that mean? If it performs work, that means it's performing work on its surroundings, right? And by convention, everything's based on what the system sees. So if the system is doing work on its surroundings, this has to be a negative sign, right? Because work is leading the system to the surroundings. All right, now what's the question? The change in internal energy of the gas. So the change in internal energy, oops, what kind of symbol is that? I need a delta. is Q plus W, right? So Q is 0, and then we're adding a negative 30.7 joules. So the change in internal energy is a negative 30.7 joules. So that means the internal energy of our system decreased as a consequence. Okay? And that happens to be D in the review document. Okay? That's much better. Cleaning with water wipes off so much easier. Those chemicals must strip something out of the, or maybe we just left some moisture on board. I don't know. Okay, 2. Let's see what 2 says. What's the kinetic energy of 1.56 kilogram object? So the mass is 1.56 kilograms. And the object is moving at 94, the velocity, 94.0 kilometers per hour. And all of the answers are in kilojoules. Okay? So we want to know the kinetic energy. So what's the formula for kinetic energy? Remember? I'm sure it's in useful information. I always stick that one in here. Let's see, where did it go? Middle column, almost to the bottom. 1/2 mass times velocity squared. Can we just insert those values in here and get the right answer? Nope. The standard units for a mass are kilograms. Right? The standard units for velocity are meters per second, and then squared. So this one's right. That's kilograms. Right? This one needs to be meters per second. So we have to convert it. Remember, when you have units that need to be converted and there's more than one unit that has to undergo conversion for a particular measurement, do one of them at a time. So we'll convert this one to meters. Kilometers is on top, kilometers on the bottom here. And the ratio is 1,000 to 1. 1,000 meters in a kilometer. So that gives us meters. Now we can go to hours. So hours is on the bottom here. Has to be on the top here. Do we know how many seconds there are in an hour? No. If you don't know, then use what you do know. Right? 1 hour is 60 minutes, right? And so the hours cancel. Leaves us with minutes. We're not there yet. We need seconds. How many seconds in a minute? Minutes. Seconds. 60 seconds. 1 minute. So now the minutes gone. Now we have meters per second. Right? So if we dive into our calculator and say 94 times 1,000 times 1 times 1 divided by 60 and divided by 60. Oops, I did something wrong. Back up. Divided, 60 divided. So I get 26.11. Yeah, 26.11 meters per second. Now we've got our units right. We can plug them in our formula. 1/2 mass is 1.56 kilograms. And then velocity is 26.11 meters per second. But that's squared. Okay? So we got to square this one, multiply it by that, divide by 2. So I've already got it in here, so let me just square it. Okay? And then multiply by 1.56, divide by 2. I get 5.32 times 10 squared kilogram meter squared per second squared, and that unit is equal to joules. Let's see if I did that right. Yeah. Okay. So this is joules. But all of our answers are in kilojoules, right? So how many kilojoules is that many joules? Well, if you know the relationship, as the units get bigger, the number gets smaller, right? So you would have to move the decimal place 3 to the left. But then where does that leave this one? You have 2 possibilities. You do this, 1, 2, 3, 0, 5, 3, 2 times 10 squared kilojoules. That would be 3 places to the left. 1, 2, 3. Then you move back to the right and store that information over here. Right. So let's see. Yeah, that's right. So these 2, I'm going to take away from here to here. And then I'm going to add 1 more, so it should be 10 to the first power. Now, if your brain is fried from studying and taking tests, this is kind of a tricky way to go about it. So the more reliable way is to use a conversion factor. Joules on the bottom, kilojoules on the top, because that's where you're headed. What's the relationship? 10 to the third, 1,000 joules in a kilojoule. Now we cancel these, those, and we have 10 to the third. Let's see. Then this should be minus 1. See what happens? If you try to do it this way, mistakes are inevitable. But if you do it this way, then 10 to the third in the denominator comes into the numerator as 10 to the minus third, and 10 to the minus third and 10 squared is 10 to the minus 1. So that means this becomes that. 5.32 times 10 to the minus 1, and that is A. Okay. I like this way better. Because that way, you're less likely to make a mistake. Okay. Let's see, let me check these off as I do them. So I'll go back and do the same one over again. Questions so far? The trick to doing these first 2 is pay attention to your signs and conversion factor. Now here's a logic question, number 3. Which of the following statements correctly describes the signs of Q and W for the following exothermic process at 1 atmosphere pressure and 370 K? So our reaction is this one as given, right? And it becomes this one and it's an exothermic process, right? So where do we put the heat or the energy for an exothermic process? If it's exothermic, the heat is a product. So there's our heat for the product. This is exothermic. Okay? So, we may not need these. 1 atmosphere and temperature is 370 K. So what are our choices for Q and W? Well, let's see. A, B, C, D, E. So the A possibilities, Q and W, are negative. So let's say, let me put Q up here, W up here. And then I'll just fill them in like that. Q and W are negative. Is that true? Well, let's look at it this way. Relative to the system, an exothermic reaction is one in which heat is leaving the system. Right? So that's true. That negative is true. But if we're going from a gas to a liquid and the pressure is constant, what's happening? Look at it this way. Right? Constant pressure, 1 atmosphere. And you've got a gas in here that's becoming a liquid. So if the pressure is constant and this gas condenses, what happens to that piston? It drops. And when it drops, that means it's doing work on the system. So that means the work has to be positive. Right? So the work should be positive. Okay, so A is out. How about B? Q is positive, W is negative. Q is positive, W is negative. Well, we just showed that this one has to be negative, so that can't be it. And this one has to be positive, so that can't be it. We've already explained that one away. Q is negative for C, and W is positive. Right? Q is negative, yep. W is positive, yep. So C is your answer. So I think the trick to this one is recognizing first an exothermic reaction is Q is negative because exothermic means it's leaving the system. Right? That's the easy side. The tricky side is recognizing that the gas is under 1 atmosphere pressure. And if it condenses, then the piston moves down and the surroundings are doing work on the system as it drops. Okay? That's the tricky part, I think, the work part. Let's see, we lost somebody. I don't know what happened. Okay, that was 3. So let me keep track of that right here. Let's see if 4 is a different concept. Okay, we can do 4. There's considerable overlap, but it won't hurt to hammer this one home. In a particular process, Q equals 20 kilojoules, and W equals 15 kilojoules. Which of the following statements is true? Now, they don't tell us what the sign is. We assume that since they're giving it to us as an equation, Q equals and W equals, that they're both positive. So if that's the case, and they're both positive, then A says heat flows from the system to the surroundings. Okay. Well, if heat flows from the system to the surroundings, Q should be negative. And it's not. It's positive. So how about B? The system does work on the surroundings. The system does work on the surroundings. Same thing, the sign should be negative. If it's doing work on the surroundings, work is leaving the system. So W should be negative, and it's not. Okay, let's see what C is. Delta E equals 35 kilojoules. There she is. Camera came back.
That one's it because you add.
No. Again?
I said that one's it because you add the kilojoules, the 20 and the 15.
Right. These are both positive. Add them together to find E. So that is 35 kilojoules. Yeah. C is an answer. D is all of the above are true. That's false. None of the above are true. That's false. So C has to be the answer. Yes, indeed. Okay. All right. Since we're on brain twisters, let's do number 5. I find it always helps to take these things from the paper and from the problem and put them on paper or on the board so it can make sense of the information. Which of the following statements is correct? Okay. And, 5. A. The internal energy of a system increases when more work is done by the system than heat was flowing out of the system. So the internal energy, they're saying it increases. Under what conditions? More work is done by the system. So work would be negative. If work is done by the system, this has to be negative. Then heat was flowing into the system. So this would be positive. So if this is greater than that, it can't be. It has to be negative. Right? Add those together, should be negative, but it's not. So that can't be it. How about B? The internal energy of the system decreases. So it decreases or becomes negative. Right? So this would be positive. When work is done on the system, so W would be positive, work is done on the system, and heat is flowing into the system. No, they're both positive, so this one has to be positive, and it's negative. Well, that one can't be it. All right, let's see, maybe C is it. The system does work on the surroundings. The system does work on the surroundings. So work on the surroundings means negative. When an ideal gas expands against a constant pressure. Right? So when our ideal gas expands, it's doing work on the surroundings. An expanding gas means work is done on the surroundings. That means negative. That was it. And all statements are true, all statements are false. Can't be, because this one is true. All righty. Let's see what else we got to brain tease a little here. 6 is a variation on the same theme. Okay, here's a calculation, number 7. In the form of a word problem. So that means we do need to pull things out and make some sense of them first. 1 mole of an ideal gas. So we've got 1 mole of an ideal gas is expanded from a volume of 1 liter, so initial volume is equal to 1 liter, to a final volume of 8.93 liters against constant pressure. So P is constant. Pressure of 1 atmosphere. Okay? How much work in joules is performed on the surroundings? Well, first of all, is work being performed on the surroundings? If work's being performed on the surroundings, then the initial should be smaller than the final, expanding. And it is. Okay. So we are expanding from 1 liter to 8.93. Okay, so the difference is final minus initial, always. 0.93 minus 1 equals 7.93 liters. And what was our formula for work? P delta V, except you gotta have a negative sign, right? Because 1 times 7.93 is a positive value. And we know that work is leaving the system, doing work on the surroundings. So W equals negative 1 times 7.93, or negative 7.93 liter atmospheres. Are we there yet? Nope, because the answer has to be in joules. So what's the conversion factor? Gotta convert it to joules. There it is. 1 liter atmosphere. 1 liter atmosphere. Right. Cancel that. Cancel that. Equals how many joules? 101. Oops. 101.3 joules. So we multiply negative 7.93 times 101.3 is 803. Negative 803 joules. Is that one of our answers? Yeah, it's B. So this is B in the review document. Any questions? You got to put what you know out here. And what's the question? And sometimes you have to draw a picture. Right? So that's why on your test, I always leave you lots of space in there for doodling. Thinking. Thinking on paper. I think I'm wearing a black shirt because I just marked myself. 7. Okay. Let's see, what's A? Calculate the work for expansion of CO2. And, nah. 7 was harder than that one. Ooh, number 9. Let's see, did I give you guys an explanation of that? Number 9. Okay. Okay. So let's break this one down. A fuel-air mixture is placed in a cylinder fitted with a piston. The original volume is 0.310 liters. When the mixture is ignited, the gases are produced and 935 joules of energy is released. All right, So the heat is 935 joules are released. Now, what happens to that energy? All of that energy is converted into work, right? So what's happening? The piston is expanding, right? Going from here up to here, right? So we're doing work on the surroundings, and the Q is equal to the amount of work done on the surroundings, right? So that W has to be negative. Right? W is negative. And the question is, to what volume will the gases expand against the constant pressure of 635 millimeters of mercury? So the constant pressure is 635 millimeters of mercury. If all of the energy released is converted to work. Okay. All that energy is converted to work. So the question is, to what volume will the gas expand? So what's the final volume? All right. So what do we need to know? Well, let's see if I got my units right. 935 joules. Yep. Okay. All right, so we've got joules here, but we're playing with liters and atmospheres, right? So we need to go backwards. We need to convert this into liter atmospheres. So negative 935 joules. And what's the conversion factor again? This is 101.3 joules per liter atmosphere, correct? Let's find out how much work that is. 935, 101.3, so I get negative 9.23 liter atmosphere. Okay? So what does that mean? Well, what do we know? We know this, we just don't know the atmospheres, right? So if we convert this to atmospheres, (635) divided by 760 is 0.8355. 0.8355 atmospheres. Okay? So this is going to be equals negative P delta V. Right? And we know P, right? So P is 0.3835 atmospheres times change in volume is equal to this value. Right? So what's delta V? It's this divided into that. So 923 divided by 8355. I get 11.05. Atmospheres. That's the change in volume. That's not the final volume, right? What's the final volume? Well, it's final volume minus the initial volume, 0.31. is actually 1105 plus 310. A 0.310. Okay. So that should be 11.36. Oops, my meters. So let's see if that's one of the answers. Number 9. Rounded off, 11.4. Yeah, that's, what is it, C? Yeah, C. Okay. Any questions? Hearing none, we'll continue. All right, that was number 9. I'm doing on time. 120. Okay, so I got 25 minutes. Stop me anytime, and we'll pick up anything that you guys want to look at. Okay, here's a tricky one. 13. Yeah, I'm skipping. Well, maybe we ought to do 10. Yeah, maybe we ought to catch 10 before I move on. So which of these statements is true of a process in which 1 mole of gas is expanded from state A to state B? So 1 mole gas expands from A to B. All right. So A, let's see what this one is. When the gas expands from A to B, the surroundings are doing work on the system. Surroundings. Work on the system. Is that true? When a gas expands, the system is doing work on the surroundings, right? So that can't be. It's just the opposite. Surroundings, the system does work on the surroundings, not the surroundings work on the system. The amount of work done in the process must be the same regardless of the path. Is that true? The amount of work done. What type of function is work? Is it a state function or a path function? This is a path function. So the amount of work done in the process must be the same regardless of the path is false. The amount of work done always depends upon the path. Just like the Q is a path function. The amount of heat, either absorbed or transferred to the surroundings, is dependent upon the path. What functions are state functions that don't depend on the path? E, enthalpy. Let's see, what else? What else have we talked about? We haven't talked about anything else, have we? So those are state functions. These are path functions, so B is false. Let's see what C has to say. It's not possible to have more than one path for a change of state. Is that true? Actually, it's ludicrous. Only one path. there was only one path from a state to a state, this wouldn't mean anything. The path wouldn't matter at all if there was only one path from a state to a state. Then those would be state functions too. There are multiple pathways that are available. It's like going from here to Charleston, from Charleston to here. You can go several different ways. You can take the turnpike, the easiest route, or you can go down through Prince and back up over on the other side, or you can drive to the gorge and then go down and go across the little bridge and then back up on the other side, and then go over and then cut across. You know, there are a whole host of different ways to get where you're going in life and in chemistry. So D, the final volume of the gas will depend on the path taken. Will it? The gas is going to be where it's going to be. The final volume is not going to change. So the final volume depends on just where it is. It goes from initial to final, go that way, or go this way. So how it gets there, it could go here, it could go like that, and then it could go back up here like this, then it could go back down here like this, and then it could go there. Right. So it's a different path, but it still ends up at the same final volume. So I guess in that respect, volume is, I wouldn't say volume is a state function. But in this case, the final volume of the gas does not depend on it. Well, by definition, it is. Volume is a state function. So the final volume depends on the path. It's false. So by process of elimination, E is the only one left, right? Unless I make a mistake in creating the answers, then E has to be it. The amount of heat released in the process will depend on the path taken. That's true. Because heat is a path function. The actual heat, evolved or absorbed, is dependent on the path. Okay, that's 10. Okay, we got about 20 minutes. So let's see, where was I headed before I interrupted myself? That was 10. We might take 2 review sessions to get through all of these. Let's see, I was going to go down to 13. According to the first law of thermodynamics, the energy of the universe is constant. That's true. Change in energy in the universe is 0. You cannot increase the internal energy of the universe or decrease it. The universe is everything there is, and the amount of energy in it is constant. You can only change forms. Does this mean that the change in E, delta E, is always equal to 0? Well, now we have, this is definitions. Delta E for the universe is constant, right? But when it says delta E here in your answers, it means delta E for the system. That was kind of tricky. That wasn't fair. The difference between, this is the first law of thermodynamics. And this is for your defined system. So the defined system, we know, is equal to Q plus W. And we know that those values can vary quite a bit. So we can eliminate A because it says yes. The rest of them are no's. We have to pick the one no that actually answers the question. Delta E does not always equal 0, but this is only due to factors like friction and heat. No, not due to friction and heat. It's due to these 2 values. That's defined for the system. So let's see which one satisfies that one. Delta E does not always equal 0 because it refers to the system's internal energy, which is affected by temperature or heat and work. So C is the best answer. I'm looking at the other system case. Delta E never equals E. Delta E never equals 0 because work is always being there. Okay, D and E are disqualified because they say never equals 0. Can delta E equal 0? Yeah. If they're equal in magnitude and opposite in sign, then they cancel one another out, and delta E is equal to 0. So D and E are disqualify themselves simply by using the word never equals the words and equals. That's 13. You guys are making me do all the talking. Almost all. I did get a response. I'll give you that much. That was good. Okay. So on page 4, we have these 14 through 17 that are probably best taken in a block. Right, because the answers for 14 and 17 are all repeated for each one. So what's true about the value of Q for that, or about W for this one, about delta E for this one, or delta H for this one, right? What is it? What's true about the value of Q? Well, A says it's greater than 0. Well, maybe it is, maybe it isn't. Oh, conditions, excuse me. Conditions. Consider a gas in 1 liter bulb. 1 liter, so that's our volume. At standard temperature and pressure. So what's standard temperature for gas? 0 degrees. And pressure is 1 atmosphere. Starting conditions. Connected to a valve to another bulb that's evacuating. Right? So this bulb is connected to another bulb by a valve, and this one is in here, and this one is a vacuum. Okay? So now what's true when you open the valve between the two bulbs? What's true about the value of Q? Does the heat change? Well, if we define this as our system, the whole thing, that's not the surroundings, that's our system, then the gas expansion this would have to be an isolated system too. Because as the gas expands, the internal heat of the system does not change. Right? So that's B. No change in Q. What's true about W? Are we doing any work on the surroundings? No, because the gas is staying inside. It's not pushing against any constant pressure on the outside. Right? So work doesn't change either. What's true about delta E? Well, if that doesn't change and that doesn't change, this can't change. Right? And what's true about the value of delta H? Well, delta H is like a potential for Q. And Q didn't change. Right? So delta H cannot change either. So under these circumstances, none of those values change. I guess everybody's okay with that. I didn't hear any screaming. Oh, can I erase it? All right. So that's 14 through 17. Ding. Let's see. here's a good one. Just a reality check. 19. So these 5 things, a little more time. Okay, mass, temperature, volume, concentration, and energy. Okay. Which of the following properties are intensive properties? That is, they don't change with the amount of stuff. Right? So while we're at it, why don't we define the capacity factors too? So which is a capacity factor? Mass changes with how much stuff you have, doesn't it? Right? So that's capacity. Temperature. Does temperature change with the amount of something you have? Not initially when you measure it. Right? You can measure the temperature anywhere in your substance, and it should be the same. So that's an intensity. Right? How about volume? Volume changes with how much you have. Right? That's a capacity factor. Concentration. If you have more of something at a given concentration, it's the same concentration. Right? So that's intensity. And how about energy? Does energy change with how much stuff you have? Well, the size of your system does determine the amount of energy that you have. Right? So this is a capacity factor too. Now, if energy increases and the volume increases, all other things being equal, then this one will stay the same. Right? So if you change the amount of energy, you got to change the amount of substance that the energy is applied to. And you get this. But these are the only 2 that are intensity factors. So that's C. 2 and 4. Let's see. We got a little more time. Number 20. This introduces a different formula than we used up to this point. It was in the PowerPoints, but here it's actually used to solve the problem. Okay, for this reaction where we're going from liquid water to gaseous water, and we're at temperature equals 298 A, and pressure is 1 atmosphere. Delta H exceeds delta E by 2.5 kilojoules per mole. Right, so this is more positive than this one by 2.5 kilojoules per mole. Okay? This quantity of energy can be considered what? Well, remember the relationship that we had before. The delta E equals delta H. No, delta H equals delta E. Delta H equals delta E plus P delta V. That's the relationship of those 2 items. So this correlates to that, that correlates to that, and this correlates to that. Right? So that amount of excess from delta E to delta H is accounted for, since the pressure is constant, it's accounted for by the expansion of the gas, going from liquid to gas. Right? So let's see which one of these answers matches that. The heat flow required to maintain a constant temperature. Now, it doesn't say anything about the heat. The work done in pushing back the atmosphere. That's the one I vote for. So the work done is minus P delta V. Right? So the work done as this gas expands is pushing back the atmosphere. It's going from liquid to gas. So as it evaporates, it's doing work on the surroundings. So that accounts for change in volume. And that energy is accounted for here. So that is let's see, B. Let's see what the others are. The difference in the HO bond energy in water compared to H2O. Are there any bonds being broken here? Not internally. There are no internal bonds here being broken. Right? This is gas. This is water as a liquid and water as a gas. So the hydrogen-oxygen bonds are unaffected. The value of delta H itself. No, the value of delta H is dependent upon these two. Right? And this is the difference. Right? So delta H has nothing to do either with it. None of these, that didn't work. Because this one satisfies the conditions. The work done in pushing back the atmosphere accounts for that difference in kilojoules per mole. All right, let's see. We have 5 minutes. It was 20. Let's see. Well, I guess we can pick up some of the more troublesome. We didn't get very far, did we? Let's see, is there one I can do in 5 minutes that actually involves a calculation?
It's okay that we didn't get very far. You went in very depth with everything that you went over.
Let's see. How about 23? That'll finish us out. So we're going to burn ethanol. It's a liquid. And it takes 3 waters. It makes 2 carbon dioxides, gas, and 3 waters as liquid. Delta H, the enthalpy of this reaction, is minus 1.37 times 10 to the third kilojoules. Lots of energy. Okay, which one of these propositions is true? One is the reaction is endothermic. Is that an endothermic reaction? What's the sign on delta H? Negative. That means this energy is being produced and released. So that can't be it. It would be positive if it were endothermic. 2. Oh, there's our other choice. Exothermic. That one's true. How about 3? The enthalpy term would be different if the water formed was gaseous. Okay. Different delta H if H2O gas. You think the enthalpy would be different if water were a gas instead of a liquid? If you release this much energy and you had liquid water, what if that were gas? It would take some of that energy to maintain this water as a gas, right? It would absorb some of that energy. So this actually would be a smaller numerical value, still negative, but it would be a smaller value here. So yes, the states do make a difference. Let's see. I left, whoops, that ain't gonna happen. Sorry. That reaction would never happen. Ethanol with oxygen yields CO2 in water. And yes, the states do matter. In fact, any of those states that change will change the enthalpy value. Okay, so if 2 and 3 are correct, that means E is the answer. Okay. All right, so we're out of time. And what I'll do is, I guess I'll just post this one as, let's put it up here. Part 1. So, Wednesday when we come in, we'll do part 2 right before we go in the lab and do our Boyle's Law lab. It's a fairly simple lab, but this one does require a formal report. Right? So you need to have your notebook set up properly so that you can do the experiment from the notebook. And, hold on a second, here we go. I got 2 things going on at once here. Yeah, so you can do the experiment from your notebook, not from the hard copy, from your notebook, and have a place in your notebook to record the data. Based on the hard copy, you can fill out your notebook with spaces for data that you need. And then if there are any pre-lab questions, you want to have those done before you come in. We can talk about those too. Okay, so we'll pick up there on Wednesday.
All right. See you Wednesday.
Okie doke. Let's see. Let's stop the recording.